Define gravitational field. It is gravitational force per unit mass. Gravitational field strength G at a distance x from the center of a uniform spherical planet of mass m is given by expression G equal Gm over x squared. G is the gravitational constant and x is greater than radius of planet. Describe the pattern of the field lines outside the planet that represent gravitational field due to the planet. Radial towards center of planet. Explain why for small changes in vertical height near surface of planet G may be assumed to be constant. Height is too much less than radius and field lines are parallel. Assume the Earth is uniform sphere. For the Earth, the product Gm is equal to 3.99 times 10 to 14. Determine a value to 3 significant fig for radius of the Earth. G for Earth is equal to 9.81. G is equal to Gm over x squared. X here will be R, so it is R squared. So for R, we can substitute and the result will be calculate gravitational potential of Earth's surface. Give unit for your answer. Phi equal minus Gm over R. So it is equal minus and the answer will be unit for gravitational potential is joule per kilogram or joule kilogram minus 1. Don't forget its definition is work done to bring a unit mass from infinity to the point, so it is work per mass unit. Explain why gravitational potential energy of two-point masses is always negative. Phi at infinity equal to 0 and Fg is always attractive. State what is meant by two objects being in thermal equilibrium means is that they have same temperature and no net heat transfer. A mass x of ice at 0 Celsius placed in a beaker containing mass m of water at T Celsius. The beaker is perfectly insulated and has negligible heat capacity. After some time, the ice that was added reaches thermal equilibrium with the original water in the beaker. The specific latent heat of fusion of water is L, the specific heat capacity of water is C, the final temperature of system is theta. Give expressions in terms of sum or all of x, m, t, theta, L, C for the thermal energy. E1 gained by the ice as it melts to become water at 0 degrees Celsius. Because it is in the melting, we have a latent heat which is calculated by multiplying the mass of the material, which is the ice here, which is X, times the latent heat of fusion, specific latent heat of fusion of water, which is L. Energy lost by water as temperature increases from T to theta. It is certainly the mass of water times specific heat capacity times the difference in temperature, which is from T to theta means T minus theta. Energy gained by the melted ice as its Celsius temperature increases from 0 to theta. It is mass of ice, okay, which is now melted, and water times specific heat capacity times the change from 0 to theta, which is theta minus 0, which is theta. Use your answer in B to show final temperature theta of system is given by. So we have the ice gained heat during melting and heat during temperature rise from 0 to theta. Both amounts of heat are taken or gained from the water which lost this amount of heat, and certainly there is no loss to the beaker, okay, or to the rounding, because it states that beaker is perfectly insulated and has negligible heat capacity. So we will equate x L plus x c theta to m c t minus theta. This is the first step. And after that, we will do some math to bring theta as a subject. Perhaps we can take mc theta to the other side in positive, okay, and we can bring this to here, to the remaining term here in negative. After that, we can take theta as a common factor. We will divide by mc plus xc, and on the other side we will have the expression wanted, just take c as a common factor. State what is meant by ideal gas. Gas that obeys BV equals nRT. T here is thermodynamic temperature, which is temperature in Kelvin. And ideal gas at pressure 1.6 times 10 to 5 Pascal has a density of 1.9 kg meter minus 3, shows that RMS speed of molecules of gas is approximately 500. We can get the RMS from either kinetic energy equal to 3 over 2 kT or B equal 1 over 3 rho C to the power 2. We can rearrange, okay, this B times 3 over rho, and we can take the square root to get the RMS, Okay, so we have here 3, and the answer will be 1 molecule of gas has mass of 4.7 times 10 to minus 26. Determine thermodynamic temperature of gas. Okay, so half m c bracket square, which is the mean square of speed of molecules, well, 3 over 2 kt. We can eliminate 2 and we can rearrange for temperature to be like that. After that, we can directly substitute with values we have. And we get 287K. Calculate the internal energy of 6 mole of the gas and explain your reasoning. So U is the sum of kinetic energies and the potential energies, and for ideal gas, potential energies is 0, so it is only sum of kinetic energies of molecules of gas. So we can get it by multiplying the number of molecules times the kinetic energy of one molecule. We have 6 moles, and Avogadro's number represents the number of molecules per mole. So this is N. After that, we have mass of molecule and C. So we can just substitute and get the answer as something like that. Okay, we certainly can write it in this form. What is meant by simple harmonic motion? Acceleration directly proportional to displacement and in opposite direction. Small sphere is suspended from a fixed point B by a string of negligible mass as shown. The sphere is given a small horizontal displacement and then released. The variation of horizontal velocity with time is shown. State 2 times at which sphere is passing in same direction through equilibrium position. So equilibrium position at which velocity is maximum, okay, whether in positive or negative direction. So we have all of these positions, T1, T3, T5, and T7, and to have the same direction. For example, here the velocity, if we take the negative direction to be to the left and the right to be the positive one, so it is here going from negative or from left to right, okay, reaching the sorry, here it is from right at T1, it was coming from right to left and reaches the equilibrium from right to left direction. After that, it will continue to left until it reaches the maximum displacement or the amplitude to the left. Okay, at this time certainly velocity will be 0. After that it will go in rightward again and reaches the equilibrium to be positive value, maximum positive value for the velocity. Okay, so we have T1 and T5. Okay, or we have T3. T3 means it reaches equilibrium position from left to right or rightward. Okay, and it goes to the maximum rightward, maximum displacement or amplitude, where it becomes a 0, the velocity. After that it goes to the left, reaching the equilibrium from the left. This is why we said this T1 and T5. After that it goes to maximum leftward, maximum displacement or amplitude. Then it goes rightward again. So T1, T5 or T3, T7. Okay. The time interval between T1 and T6 is 2.2. Calculate frequency of oscillation of the sphere. So from T1 to T6, it is one complete wave. Sine wave can be analyzed to 4 sections, 1, 2, 3, 4. This is the first wave, and to T6 it is another quarter, so it is 1.25 T periodic time of one period, that equal to 2.2, and we can divide and find that T is equal to 1.76 seconds, and the frequency is the inverse or reciprocal, so it is 0.57. The sphere is undergoing a simple harmonic motion. Use your answer and data to determine maximum displacement of the sphere from its equilibrium position. So maximum displacement, which is x naught, and we have both velocity, maximum velocity, and frequency. It is really simple if we remember this relation v equal omega x naught square minus x square. V maximum is at x equals 0 at the equilibrium, so it equals to omega x naught. Omega is 2 by f. We have just calculated f, and x naught is what we want. So we can rearrange, substitute, and find the answer to be like that. Electric potential at a point, same as gravitational potential. It is work done per unit charge. In gravitational potential, it is unit mass, to bring a charge from infinity to the point. An isolated solid metal sphere of radius r is given a positive charge. The potential at surface of a sphere is 9 times 10 to 4 volt. At a distance 3r from the center of the sphere, the electric field strength is 2 times 10 to 5 Newton, column minus 1. Determine electric field strength at surface of sphere. So we have electric field strength at 3r, but we have potential at surface of a sphere. We know that E is equal to kq over r squared, which means it inversely proportional to r squared, distance squared. So we can write E1 over E2 equals E1 is equal to E2. E1 is field strength at the surface. E2 is field strength at 3r. So E1 is equal to E2, okay, times R2 square over R1 square. R2 is 3R, R1 is R, all squared. R can be eliminated. So we have this number times 9 is equal to 1.8 times 10 to 6. Show that radius of a sphere is 5. We have V equal KQ over R, and we have E equal KQ over R squared. So E equal V over R. We have the potential at surface and field at surface. So from this relation, we can simply get R as potential divided by field at surface we have just calculated. So we get 0.05 meter. Calculated charge on a sphere from V equal KQ over R. We can find that Q equal VR over K. K is 9 times 10 to 9, and we get K from the relation 1 over 4 pi epsilon naught. Okay. You will find this constant in the formula sheet. So the answer here will be C is column, certainly. Use your answer to determine the capacitance of the sphere. We have C equal Q over V. We just calculated Q, and we have V, so we can get C as farad. Rectangular coil of wire is free to rotate about its axis. The coil length QR is 5.4 centimeter. Width BQ is 2.5, 190 turns. Plane of coil is at angle theta to uniform magnetic field of flux 5.2 of flux density 5.2 times 10 to minus 3 Tesla. The axis XY of coil is normal to the field. Okay, the current in coil is 1.2 ampere. Calculate force on side QR. So side QR is in a plane perpendicular to the field plane. So we can apply the formula F equals BIL and substitute easily from the values given. L here is the length of QR, which is 5.4 centimeter. But don't forget that we have 120 turns. So we have the final answer in Newton. Use your answer to show that the torque tau on coil is given by 1.6 times 10 to minus 3 cosine theta Newton meter. We know that torque is force times perpendicular distance from the pivot, which is the axis of the coil here. This is our pivot, so we need this distance. Okay. And this distance if the plane of coil is parallel to the plane of field but at any angle theta, this distance will be the perpendicular distance. And how we can get this distance? Certainly from theta. We have theta to be cosine theta to be high to be neighbor, okay, which is the perpendicular distance that we want to use in the formula, over the hypotenuse, which is BQ over 2. Okay. So for the torque, we have F that we have just calculated on QR times the distance, perpendicular distance I have just showed to you. The perpendicular equals cosine theta BQ over 2, but this will give the torque on side QR. As coil rotates, there are another torque on side BS. So the total torque on the coil is 2 times the force times the perpendicular distance. Okay, so we have here 2 times the force. Perpendicular distance is 0.025 over 2, which is the side here BQ over 2, and here is the cosine theta. Certainly 2 can be eliminated with 2, and if we multiply these two numbers, we will get the number here. Using the expression in EII sketch on axis of figure 6.2 a graph to show the variation of torque tau with angle theta for values of theta between 0 and 360, label tau axis with an appropriate scale. So we have some value. This will be our amplitude. We can make it here, and we have the times minus 3 on the axis, and it will be a cosine function that is maximum at 0 and 0 at 90. So we will just draw standard cosine function. Here is minus 1.6 because cosine goes from 1 to negative 1. Okay, negative 1 at 180 goes back to 0 at 270 and to maximum again at 360. The coil is now replaced by an identical coil wound on a ferrous core, suggest with a reason how the torque on this coil compares with the torque on the original coil. So ferrous core makes flux increases, and as flux increases, this will make the torque greater, okay, because torque was force times perpendicular distance. Certainly perpendicular distance will be the same because we didn't change the geometry of the coil, so it is only the magnetic force that will change, and magnetic force is BIL. Current that didn't change, length didn't change, so it is only the B, which is related to phi, BA equal phi. So as phi increases, certainly torque, force will increase and torque will increase. A bar magnet is suspended from a spring. One pole of the magnet oscillates freely in a coil of wire. The switch is initially open. The switch is now closed. As a result, oscillation of magnet are highly damped. State what is meant by damping: a decrease in energy of oscillation because of the resistive forces. Describe what is observed to indicate the damping is light. Oscillation continues. By reference to EM induction and the conservation of energy, explain why oscillation are damped. Oscillation changes phi with respect to time, which leads to induced EMF or induced current. Current in resistor causes energy loss in form of heat. Okay, current induce the current in coil when flows through the resistor, switch is now closed, will cause a energy loss in form of heat, and certainly this energy is oscillation energy. The procedure in A is repeated after replacing the resistor with one of a greater resistance. Suggest with a reason the effect of this change on the oscillation. So as resistance increases, the current in the circuit will decrease. As R increases, current decreases, and energy loss will decrease as current decreases. Okay, remember, B, power energy loss, is equal to I squared R. Okay, R decreases and R increases. We can not predict by this formula. We can use we can use V squared over R as V, which is the induced EMF related to rate of flux change. Rate of flux change didn't change because the oscillation of the spring didn't change. So phi, delta phi by delta t didn't change, and induced EMF didn't change. So V is constant, just R changed. Okay, so V constant, R increases, V squared over R decreases. So heat loss decreases. Energy loss in form of heat decreases. Complete circuit diagram of bridge rectifier. Sorry. Here is one diode, here is the other. All towards the left. You can check here. Here is positive. Go for here. This is closed. This is open. So here is positive. And if here is negative, it will not go through this branch, only through this branch. And when it reaches here, this is closed, so it will go to this, keeping the polarity the same. Always here is positive and always here is negative. Variation with time of potential difference across load resistor is shown. A capacitor is now connected between C and D of the bridge rectifier. This results in smoothing of potential difference across the load resistor. Difference between max and min values of smooth BD is 33% of peak BD V node. On figure 8.2, draw line to show variation of BD across the load resistor with time. Your line should extend from 0.5 T capital periodic time to 2 T capital. So as the capacitor causes a difference between min and max value to be 33% of V nodes. Okay, so from maximum to minimum, we should have the third of this distance. And if we looked carefully here, we can find that there are, let me increase, we have 3 small square, 3 small square, so 33% is third, this distance is 30% of V naught, so it is this small square that is the difference between max and min. Okay, so we can make by the rule connection like that, and certainly increase the curve here and continues like that. Okay, here is this last one. Okay, use your line to determine in terms of t the time constant of the smoothing circuit. So we have V over V naught to equal EO to the power minus T over tau. Tau is the time constant here. Ln 2 over 3. Why 2 over 3? Because at a time between 0.5t and 1t, which is 0.5t, value changed from V naught to 2 over 3 V naught. Okay, so this is 1 over 3 V naught, this is 2 over 3 V naught, and you can, as we have just discussed, that the difference between max and min is just 1 over 3 V naught. Okay, so from V naught to 2 over 3 V naught, this happens in 0.5t. So we have here okay, and sorry, it's not 0.5 t is the time during which this change happened. It is from 0.5 t to before the 1t by 1, 2, 3, 4 small squares. So from 0.5 t to 1 t, it is 3 small squares, which means 15 very small square. Okay, this represent 0.5 t. So one very small square is represented by 0.5 over 15 t, which is 0.37 t. When we multiply the value here by this 15 minus 1, 2, 3, 4 very small square, we will get that the time is 0.370. After that, it is a sample rearrangement that can bring us the answer. it will be 0.9 T-cut. The resistance of load resistor is now increased. The capacitance of the capacitor is unchanged. State and explain the effect of this change on smooth output potential difference. So as resistance increased, tau increased, because tau is RC and R increased. And as tau time constant increase, this means that difference between max and min potential difference, okay, will decrease, okay, because it is related to the time constant. What is meant by wave particle duality? EM wave, electromagnetic wave, behaves as particle and moving particle behaves as wave. State relation between the Pauli wavelengths and momentum. State any other symbol. B equals h over lambda. H is Planck's constant. A narrow beam of electrons, all with same speed, is incident normally on a carbon film. The electrons then move onto a fluorescent screen. The apparatus is in vacuum. Pattern produced on screen is like that. Explain why the pattern provides experimental evidence to indicate a wave nature of the electron. Certainly the pattern is diffraction pattern. And bright and dark rings are for constructive and destructive interference. Speed of electrons is increased, suggests to the reason how this change affects the pattern observed on the screen. So as the speed increases, lambda decreases because momentum increases, and relation between momentum and lambda is inverse relation, so lambda decreases. And when lambda decreases, you remember from AS level, rings become closer, okay, because distance to the ring is related to the wavelength used. Describe how piezoelectric crystal in transducer generates ultrasound waves for use in medical diagnosis. We have AC potential difference that makes crystal vibrates, and AC potential difference frequency is equal to natural frequency of crystal, okay, piezoelectric crystal. So crystal resonates and crystal, if not at which the resonance happens, is in ultrasound range. A parallel ultrasound beam is incident on a boundary between two media. the media have a specific acoustic impedance Z1 and Z2. As a boundary, a fraction alpha of incident intensity is reflected. The remainder is transmitted. State what is meant by specific acoustic impedance. Z is equal to rho times C. Rho is density of medium, and C is sound or ultrasound speed in medium. Describe how alpha depends on relative values of Z1 and Z2. Alpha is equal to IR over I naught, so it is equal to Z1 minus Z2 over Z1 plus Z2. For Z1 equal to Z2, alpha is 0, no reflection at all. If Z1 is too much greater or too much less than Z2, alpha approaches 1, which means that there is a great reflection between or at the boundary. A parallel ultrasound beam of intensity I naught enters a region of soft tissue after passing a distance of 2.1 centimeter through the tissue. The intensity of ultrasound is 0.62. I naught. Calculate linear attenuation coefficient and give the unit. We have I equal I naught e to power minus mu x. So we have ln I over I naught equal to minus mu x. So we have mu equal minus 1 over 2.1. I'll leave it in centimeter because I want the unit to be centimeter minus 1. And the ln here will be ln for 0.62. The answer will be deuterium has mass of in U. Helium has a massive effect, and helium has a massive effect also on U. Helium formed from deuterium in nuclear reaction can be represented. We have 3 deuterium here that form helium, a proton and neutron. State name of this type of nuclear reaction, it is fusion. Show energy released when one nucleus of helium is formed from deuterium is. To find this, we should find firstly the mass defect of the reaction. It will be the mass defect of helium minus that of 3 deuterium. Okay, because as we know, for any reaction to go in one direction, this means that we have increase in binding energy per neutron, and binding energy is given from delta M mass defect, so we should have a mass defect on the right side that is greater than on the left side, okay, for reaction to go like this. So I'll write this large number and make the calculation to find the mass defect through the wall of reaction. Okay, After that, I'll get the energy released as difference as this difference multiplied by speed of light squared, but before this we should convert it to kilogram to have our units all in SI unit, and we will get E to be like okay. A star has a radius 6.96 times 10 to 8. Helium is produced inside the star from deuterium at a mass rate of 7.34 times 10 to 11 kg second minus 1. All the, the energy released from this process is radiated away from the star. All the energy that is radiated from the star is released by this process. Calculate the luminosity of a star. Okay, we know that luminosity is energy per time, and for this reason it has a watt unit. This is a power quantity. So we need the energy obtained from this mass in 1 second to get the luminosity. So we need to know this mass represent how much helium atom or helium nucleus produced. And we know the energy for a helium produced from this fusion reaction. So we simply get the answer. So we will start first by knowing 7.34 times 10 to 11 represent how much moles. And we will multiply this number by Avogadro's number. We get all number of helium atoms involved, and after that multiply by energy from one helium atom. So I'll divide this by molar mass of helium, which is 4 gram. I need certainly to convert it in kg because this number is in kg. I'll get 1.84 times 10 to 11 mole. This is in seconds. Multiplying it by Avogadro's number and by energy for one atom or one nucleus formed, we will get the answer as determine the surface temperature of the star. We have Stephen Boltzmann relation. We will rearrange for T as a subject, so we will have all to power 1 over 4. We will substitute luminosity, and here you can use your calculator, the fraction button, to make this calculation just in one step. But perhaps you need a quite recent calculator because old ones, very old ones, will not get this option. And final answer will be. Thank you for watching. Keep following.